tonight, as you settle in and allow the day to gently loosen its grip, imagine yourself floating far beyond Earth, past the familiar glow of city lights, past weather systems and satellites, past the calm blue curve of our planet. You drift outward, slowly, comfortably, into the wider universe. This is a place without rush, without noise, where even the most powerful forces move with patience measured in millions of years. In this quiet expanse, we begin a gentle journey into one of the most fascinating subjects in modern astronomy: black holes. Black holes often sound dramatic, even frightening when we first hear about them. They are described as regions where gravity is so strong that nothing can escape, not even light. But tonight, we will approach them differently, calmly, slowly, with curiosity instead of fear. Like astronomers who spend entire careers studying these objects, not because they are dangerous, but because they are deeply beautiful expressions of how the universe works. As you listen, there is nothing you need to remember, nothing you need to understand perfectly. These black hole facts are offered softly, like stars passing by your window. Take what you like. Let the rest drift away. This is astronomy for sleep. If you enjoy calm educational journeys like this, you're welcome to like the video or subscribe to the channel. And if you feel like it, you can leave a comment sharing your country, your city, and the time you're listening. Many people around the world are listening quietly, just like you, under the same sky. Now, let's begin with a peaceful truth. Despite their name, black holes are not holes in space. They are not cosmic vacuums roaming the universe and swallowing everything in their path. A black hole is actually an object. It has mass, it has location, and like stars or planets, it follows the laws of physics. The term black hole simply describes what happens when matter is compressed into an incredibly small space, creating gravity so strong that light itself cannot escape. The idea of black holes grew gradually from mathematics, not observation. In the late 18th century, scientists like John Mitchell and Pierre-Simon Laplace wondered what would happen if a star became so massive that its gravity trapped light. At the time, this was a thought experiment, a quiet mathematical curiosity. There was no telescope powerful enough to test it. The universe, however, was already full of answers, waiting patiently. Black holes form when massive stars reach the end of their lives. Stars spend most of their existence in balance. Gravity pulls inward, while nuclear fusion pushes outward. This balance creates light, warmth, and stability. But when a very large star runs out of fuel, that balance fades. Gravity wins. The core collapses inward, and in some cases, it collapses so completely that a black hole is born. This process doesn't happen quickly from a cosmic perspective. It unfolds over thousands or millions of years, part of the natural life cycle of stars. In this way, black holes are not symbols of destruction, but of transformation. They are a quiet reminder that the universe recycles everything, even the most massive stars. One of the most calming facts about black holes is that they are incredibly far away. The closest known black hole to Earth is more than 1,000 light-years distant. A light-year, by the way, is not a measure of time, but of distance. It represents how far light travels in 1 year, nearly 10 trillion kilometers. They are distant landmarks in a vast cosmic landscape. In fact, if our sun were magically replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. The gravitational pull would remain the same. The difference would be that the sun's light and warmth would disappear. This simple comparison helps astronomers explain that black holes don't pull more strongly than objects of equal mass. They are extreme, yes, but they are not monsters. At the center of our own galaxy, the Milky Way, there is a supermassive black hole called Sagittarius A*. It has a mass about 4 million times that of the Sun. Despite this enormous mass, it remains surprisingly quiet. It is not actively consuming large amounts of matter. Instead, it sits calmly, influencing the motion of stars around it like a silent conductor guiding a slow orchestra. Many galaxies appear to have supermassive black holes at their centers. This suggests a deep connection between black holes and galaxy formation. Some scientists believe galaxies and their central black holes grow together, shaping each other over billions of years. This relationship ties black holes to cosmic history, to the story of structure, movement, and balance on the largest scales imaginable. Black holes themselves are invisible. We cannot see them directly because light cannot escape from within a boundary called the event horizon. The event horizon is not a physical surface. It is a mathematical boundary, a point of no return. Crossing it doesn't feel dramatic in theory, especially for a very large black hole. Physics suggests that at that boundary, nothing special happens locally. Space simply curves more steeply. We detect black holes by their effects on nearby matter. When gas or dust falls toward a black hole, it heats up, forming a glowing disk called an accretion disk. This disk can shine brighter than entire galaxies, especially around supermassive black holes. Astronomers use X-ray telescopes and radio observatories to study these glowing signatures, turning invisible objects into measurable science. In 2015, humanity made one of its most peaceful scientific discoveries related to black holes. Scientists detected gravitational waves for the first time. These are gentle ripples in spacetime created when massive objects, like black holes, collide. The signal that reached Earth came from two black holes merging more than 1 billion years ago. By the time the ripples reached us, they were incredibly faint, passing through our planet without harm, like a whisper from the distant past. This discovery confirmed predictions made by Albert Einstein a century earlier. It also opened a new way of listening to the universe. Instead of only seeing space, we can now hear it in a sense. Astronomy has become both visual and acoustic, expanding human knowledge in a quiet, profound way. As you rest here, listening, it's comforting to know that black holes follow rules. They obey mathematics. They respect conservation laws. They are not chaotic anomalies, but precise outcomes of physical processes. In a universe filled with uncertainty, black holes represent consistency on the grandest scale. And perhaps that is why learning about them can feel strangely calming. They remind us that even the most extreme things in nature are part of an order, part of a story that unfolds slowly, patiently, and without urgency. As you continue to relax, imagine yourself drifting a little farther into space. The stars are more spread out here, the darkness deeper, the silence wider. In this calm environment, we begin to notice that black holes are not all the same. Just as planets come in different sizes and stars live very different lives, black holes also exist in several distinct forms. Understanding these types helps astronomers map the structure of the universe. And it also gives us a gentle sense of scale, from the small to the unimaginably vast. The most common type of black hole is called a stellar mass black hole. These form from the collapse of massive stars, typically ones that were at least 8 times more massive than our Sun. When such a star reaches the end of its life, it may explode in a supernova, briefly becoming brighter than an entire galaxy. After this dramatic moment, the remaining core collapses inward, forming a black hole with a mass several times that of the Sun. Stellar mass black holes are relatively small in cosmic terms. Their event horizons can be only a few tens of kilometers across. That may sound tiny, but remember that all the mass of several suns is compressed into that space. These black holes are scattered throughout galaxies, including our own Milky Way. Astronomers estimate that our galaxy may contain millions of them, quietly orbiting the galactic center, mostly unnoticed. Many stellar mass black holes are found in binary systems paired with a normal star. As the black hole orbits its companion, it can pull gas from the star's outer layers. This gas spirals inward, forming a glowing accretion disk. As it heats up, it emits powerful X-rays. These X-rays are one of the primary ways astronomers detect black holes, turning invisible gravity into visible data. Another category is known as intermediate mass black holes. These are something of a cosmic mystery. They are larger than stellar mass black holes, but smaller than supermassive ones, typically ranging from hundreds to tens of thousands of solar masses. For many years, scientists debated whether they truly existed or were just theoretical stepping stones. In recent decades, evidence for intermediate mass black holes has grown stronger. Observations of dense star clusters, especially globular clusters, suggest that some of them may host black holes in this mass range. These objects could represent an important phase in cosmic evolution, perhaps forming from repeated mergers of smaller black holes or from the collapse of unusually massive early stars. Then there are the giants, supermassive black holes. These are the most massive objects of their kind, with millions or even billions of times the mass of the Sun. Almost every large galaxy studied so far appears to host one at its center. Our own Milky Way's central black hole, Sagittarius A*, is relatively modest compared to some others, but it still outweighs millions of stars combined. Supermassive black holes play a central role in galaxy evolution. They influence the motion of stars, regulate the flow of gas, and can even affect star formation. When actively feeding, they power phenomena known as active galactic nuclei and quasars. These are among the brightest objects in the universe, visible across billions of light years and important tools for studying the early cosmos. Despite their size, supermassive black holes are surprisingly gentle neighbors most of the time. Sagittarius A*, for example, is currently quiet. Stars orbited peacefully, completing their paths over decades and centuries. Astronomers track these stellar orbits carefully, using them to measure the black hole's mass with remarkable precision. This calm dance of stars provides one of the strongest pieces of evidence for the existence of supermassive black holes. There is also a hypothetical category known as primordial black holes. These are thought to have formed not from stars, but directly from dense regions in the early universe shortly after the Big Bang. If they exist, primordial black holes could range in size from tiny subatomic masses to much larger objects. Some scientists have even suggested that they could make up a portion of dark matter, the mysterious substance that shapes galaxies but does not emit light. So far, primordial black holes remain unconfirmed. But their study connects black holes to cosmology, particle physics, and the earliest moments of time. Even as theories, they add depth to our understanding of how flexible and creative the universe can be. One calming realization is that black holes grow slowly. They do not appear overnight. Stellar mass black holes grow by consuming gas or merging with other black holes. Supermassive black holes grow over billions of years, gradually accumulating mass from their surroundings. This slow growth mirrors the pace of cosmic history itself, steady and patient. In the world of astronomy, black hole mergers are especially important. When two black holes orbit each other, they gradually lose energy through gravitational waves. Over time, they spiral closer and closer until they merge into a single, larger black hole. These events release enormous amounts of energy. But by the time the waves reach Earth, they are incredibly subtle, detectable only with the most sensitive instruments ever built. The detection of these mergers has transformed astronomy into a form of cosmic listening. Facilities like LIGO and Virgo act as observatories, not of light, but of motion in spacetime itself. This technology represents a blend of education, advanced technology, and global scientific cooperation, bringing together researchers from many countries to study the universe peacefully. Black holes, despite their reputation, are not destroyers of order. They are participants in it. They help redistribute energy, shape galaxies, and preserve information in ways physicists are still working to understand. Even Stephen Hawking, who dedicated much of his life to studying black holes, emphasized that they are not eternal prisons. Over extremely long timescales, black holes may slowly evaporate through a process now known as Hawking radiation. This idea suggests that even black holes are temporary, lasting for vast spans of time, but not forever. The universe changes everything, eventually. There is something quietly comforting about that thought, a reminder that all things, even the most massive, are part of a gentle cycle. As you rest and listen, let these ideas settle softly. Picture stellar mass black holes drifting through galaxies, intermediate ones hidden in clusters, and supermassive giants anchoring the cosmic web. They exist not as threats, but as natural landmarks in the geography of space. As you continue to rest, imagine the universe as a vast, quiet ocean. Instead of water, this ocean is made of space and time woven together into a single fabric. In this gentle mental image, black holes are not holes at all, but deep curves in that fabric, places where the cosmic ocean dips and bends under immense weight. Understanding this idea helps transform black holes from frightening mysteries into elegant features of nature's design. The concept that gravity shapes space and time comes from Albert Einstein's theory of general relativity. According to this theory, massive objects do not simply pull on other objects through invisible forces. Instead, they bend the geometry of spacetime itself. Planets follow curved paths because space around stars is gently warped. In the case of black holes, this warping becomes extreme. Near a black hole, spacetime curves so deeply that familiar ideas like distance and duration begin to change. Time slows down in strong gravitational fields, a phenomenon known as gravitational time dilation. If you were watching a clock fall toward a black hole from a safe distance, you would see it ticking more and more slowly. From the clock's own perspective, however, time would seem normal. This stretching of time is not just theoretical. It has been measured near Earth using precise atomic clocks on satellites, and the effect becomes stronger near denser objects. Black holes simply take this principle to its natural limit. In this way, black holes serve as laboratories for understanding time itself, something that links astronomy, physics, and education in profound ways. The event horizon marks the boundary where space-time curvature becomes so steep that nothing can return. Outside the event horizon, objects can still escape if they have enough energy. Inside it, all paths lead inward. Importantly, the event horizon is not a solid surface. An astronaut crossing it would not feel a sudden jolt or barrier, at least not for very large black holes. One of the most fascinating predictions of general relativity is that black holes cause something called frame dragging. When a black hole spins, it pulls space-time around with it, like honey swirling around a spoon. This effect has been measured near Earth using satellites, but near rotating black holes, it becomes incredibly strong. Space itself is carried along in the direction of the spin. This spinning motion affects everything nearby, including matter in accretion disks and even light. It can shape powerful jets that shoot out from the regions near black holes at nearly the speed of light. These jets can extend for thousands or even millions of light years, influencing the structure of entire galaxies. Despite their dramatic appearance, these processes unfold slowly over cosmic timescales. Light behaves in unusual ways near black holes. Because space-time is curved, light does not travel in straight lines as we normally imagine them. Instead, it follows the curved geometry around massive objects. This bending of light is called gravitational lensing, and it allows astronomers to observe distant galaxies magnified and distorted by black holes and other massive structures. In some cases, light can orbit a black hole briefly before escaping. This creates a bright ring around the black hole's shadow, an effect famously captured in the first ever image of a black hole released in 2019. That image, produced by the Event Horizon Telescope, was not just a scientific achievement, but a global collaboration involving advanced technology, shared data, and international cooperation. The black hole image showed a dark center surrounded by glowing gas. The darkness was not the black hole itself, but its shadow, the region where light could no longer reach us. This visual confirmation helped turn abstract equations into something almost tangible, reinforcing the idea that black holes are real objects shaping the universe we inhabit. Another strange effect near black holes is the stretching of objects, sometimes poetically called spaghettification. As an object falls toward a small black hole, gravity pulls more strongly on the closer parts than on the farther ones. This difference can stretch objects lengthwise. For supermassive black holes, however, this effect happens much deeper inside, making the crossing of the event horizon relatively gentle in theory. Space and time exchange roles near a black hole. Inside the event horizon, moving forward in time becomes as unavoidable as moving toward the center. This idea challenges everyday intuition, but it follows naturally from Einstein's equations. For physicists, black holes provide a testing ground for ideas that may eventually unify gravity with quantum mechanics. At the very center lies the singularity, a point where density becomes infinite and current theories break down. Scientists do not believe nature truly contains infinities. Instead, the singularity marks the limit of our understanding. It signals where new physics is needed, possibly involving quantum gravity or other future discoveries. Thinking about singularities can feel overwhelming. But there is also something peaceful in recognizing the boundaries of human knowledge. Black holes remind us that mystery still exists, that the universe holds depths yet to be explored. This sense of wonder fuels research, education, and technological progress, quietly pushing humanity forward. Even though black holes distort space and time dramatically, their influence is localized. At great distances, they behave like any other object of the same mass. This means that if our sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. Life would be affected by the loss of sunlight, not by gravity. This fact often surprises people and helps demystify black holes. They are not cosmic vacuum cleaners roaming the universe. They are stable, predictable objects governed by well-tested laws of physics. Their exotic behavior appears only when you venture very close, far beyond where planets or stars normally roam. As you breathe slowly and let your thoughts drift, imagine spacetime as a soft fabric gently curving under the presence of stars and black holes alike. These curves guide motion, shape galaxies, and tell light where to travel. Black holes are simply the deepest curves of all. As your thoughts drift gently onward, imagine a massive star nearing the end of its long and luminous life. For millions of years, it has balanced to opposing forces. Deep in its core, nuclear fusion pushes outward, creating light, heat, and the energy that supports planets, life, and even the rhythms of cosmic travel and time. At the same time, gravity pulls inward, patiently and constantly. For most of a star's life, these forces exist in harmony. Hydrogen fuses into helium, releasing energy that resists collapse. But stars are not infinite. When a very massive star, at least 8 times the mass of our Sun, begins to run out of nuclear fuel, the balance slowly fades. Fusion slows, and gravity starts to win. The star's core contracts under its own weight, growing denser and hotter. In its final moments, heavier elements, like iron, build up in the core. Iron fusion does not release energy, and so the outward pressure weakens further. In a sudden and dramatic event, the core collapses in on itself. This collapse triggers a powerful explosion known as a supernova. For a brief time, a single star can shine brighter than an entire galaxy, releasing immense energy into space. These explosions scatter heavy elements like gold, uranium, and oxygen into the surrounding cosmos, enriching future stars, planets, and even life itself. In this way, black holes are connected to the very materials that make up our world. After the supernova, what remains depends on the mass of the original star. If the core is not too massive, it may become a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But if the core is heavy enough, not even neutron pressure can stop the collapse. When gravity overwhelms all known forces, the core continues to shrink. Space and time bend more sharply with every moment. Eventually, the collapsing core forms a black hole. An event horizon appears, sealing off the interior from the rest of the universe. From that moment on, the black hole exists as a quiet remnant of a once brilliant star. These stellar mass black holes typically range from a few times the mass of the Sun to several dozen solar masses. They are among the most common types of black holes in the universe, scattered throughout galaxies like faint, invisible embers of stellar evolution. Black holes formed this way often remain near the regions where stars are born and die, such as spiral arms of galaxies. They may drift silently through space, interacting only through gravity. Some are isolated, while others are part of binary systems, orbiting a companion star. In binary systems, black holes can reveal their presence more clearly. As the black hole's gravity pulls material from its companion, that material forms an accretion disk, heating up and glowing in X-rays. Observatories in orbit around Earth, using advanced technology and international collaboration, detect these X-rays, allowing astronomers to identify black holes indirectly. One famous example is Cygnus X1, one of the first strong black hole candidates ever discovered. It resides in our Milky Way galaxy and has helped scientists understand how black holes form and behave. Discoveries like this highlight the connection between theoretical physics and observational astronomy, showing how careful measurement transforms invisible phenomena into scientific knowledge. Not all black holes formed from stars are alike. The mass of the original star, its chemical composition, and its rotation all influence the final black hole. Some spin rapidly, dragging spacetime around them. Others rotate more slowly, offering different environments for surrounding matter and light. In recent years, astronomers have also detected pairs of black holes merging together. These events produce ripples in spacetime called gravitational waves. Detectors like LIGO and Virgo measure these faint signals, confirming predictions made decades earlier by Einstein. Each detection is a whisper from the universe, telling a story of distant black holes colliding far beyond our galaxy. These mergers show that black holes can grow over time. When two black holes combine, the result is a larger black hole with more mass and energy. This gradual growth may help explain how some black holes reach enormous sizes, especially in dense regions of space. Stellar black holes also play a role in shaping their surroundings. Their supernova origins inject energy into galaxies, influencing star formation rates and the structure of interstellar clouds. Even after their birth, black holes continue to affect their environment through gravity and radiation, connecting them to the broader story of galactic evolution. It's worth remembering that black holes do not form randomly. Their creation follows precise physical laws that scientists study through equations, simulations, and observation. This predictability is part of what makes them so fascinating. Even in the most extreme conditions, nature follows rules that we can gradually learn and understand. As you rest, imagine the life cycle of a massive star unfolding slowly over millions of years. Its light warms distant planets, supports potential life, and contributes to the beauty of night skies. When its life ends, it does not vanish. Instead, it transforms, leaving behind a black hole that carries its mass and memory forward in time. There is something calming in this continuity. Matter and energy are never truly lost. They simply change form. Black holes are not symbols of destruction alone, but markers of transformation, linking beginnings and endings across the vast scale of the universe. As your breathing slows and your thoughts become lighter, imagine drifting toward the quiet center of a galaxy, far from the bright spiral arms and glittering star clusters. There is a calm yet powerful region where gravity gently orchestrates the motion of billions of stars. At the core of nearly every large galaxy lies a supermassive black hole, an object so massive that its influence shapes the entire galactic structure. Supermassive black holes are vastly larger than the stellar black holes formed from dying stars. Instead of weighing a few times the mass of the Sun, they can contain millions or even billions of solar masses. Despite this enormous mass, they occupy a surprisingly small region of space, compressing unimaginable amounts of matter into a compact volume. Our own galaxy, the Milky Way, hosts a supermassive black hole at its center, known as Sagittarius A star. This black hole has a mass about 4 million times that of the Sun. It resides roughly 26,000 light-years from Earth, hidden behind dense clouds of dust and gas. Although we cannot see it directly, its presence is revealed through the motion of nearby stars, which orbit an invisible but extremely massive object. Astronomers have spent decades carefully tracking these stars, using advanced telescopes and precise measurements. Their orbits follow clear gravitational rules, providing strong evidence that a supermassive black hole lies at the center. This research earned international recognition and helped confirm theories about black holes that were once purely mathematical. One of the most fascinating questions in modern astronomy is how supermassive black holes form. Unlike stellar black holes, their origins are still not fully understood. Several theories exist, each offering a different path to immense mass. One idea suggests that supermassive black holes began as smaller black holes in the early universe, growing over billions of years by merging with other black holes and consuming surrounding gas. Another theory proposes that they formed directly from the collapse of enormous clouds of primordial gas, skipping the usual star formation process altogether. There is also evidence that the growth of galaxies and their central black holes is deeply connected. Observations show a strong relationship between the mass of a galaxy's central black hole and the size of its bulge of stars. This suggests a kind of cosmic partnership where black holes and galaxies evolve together over time. When supermassive black holes actively feed on surrounding material, they can become some of the brightest objects in the universe. As gas and dust spiral inward, they form a glowing accretion disk that emits intense radiation across the electromagnetic spectrum. These energetic regions are known as active galactic nuclei. In extreme cases, active galactic nuclei become quasars, objects so luminous they can outshine entire galaxies. Quasars were far more common in the early universe, when galaxies were rich in gas and black holes had abundant fuel. Today, they serve as distant beacons, helping astronomers study the early stages of cosmic history. Despite their power, supermassive black holes are not constant destroyers. Much of the time, they are relatively quiet, gently influencing their surroundings through gravity. In fact, the Milky Way's central black hole is currently calm, consuming very little material and emitting minimal radiation. This quiet nature contributes to the stability of galaxies. The gravitational presence of a supermassive black hole helps organize stellar orbits near the center, contributing to the overall structure of the galaxy. Rather than tearing galaxies apart, these black holes often help hold them together. Supermassive black holes also play a role in regulating star formation. When they become active, the energy they release can heat or expel gas from the galactic center. This process can slow or stop the formation of new stars, influencing the long-term evolution of the galaxy's economy of matter and energy. In recent years, astronomers achieved a remarkable milestone by capturing the first direct image of a black hole's shadow. This achievement required international cooperation, advanced technology, and years of careful planning. It demonstrated how modern science blends physics, engineering, and global collaboration to explore even the most extreme corners of nature. Supermassive black holes are not evenly distributed across the universe. They appear to be most common in large, mature galaxies. Smaller galaxies may host less massive black holes, or in some cases, none at all. Understanding these differences helps astronomers trace the history of galaxy formation and cosmic structure. As you rest, imagine the slow dance of stars around a galactic center. Each orbit is shaped by gravity acting over millions of years, creating patterns that remain stable and predictable. The supermassive black hole at the center is not a threat, but a silent conductor, guiding the motion of the cosmic orchestra. There is a quiet beauty in this idea. At the largest scales, the universe is not chaotic, but orderly, governed by laws that allow galaxies to persist for billions of years. Even the most extreme objects contribute to balance and continuity. As your thoughts drift more slowly now, imagine approaching a boundary that cannot be crossed in any ordinary way. Not a wall, not a surface, but a limit defined by gravity itself. This boundary is known as the event horizon, and it marks the point around a black hole beyond which nothing can return. The event horizon is often described as the point of no return. Once any object, particle, or even light itself crosses this invisible boundary, it is forever trapped by the black hole's immense gravitational pull. From the outside, however, the event horizon appears calm and unremarkable. There is no solid surface, no sudden flash, only a quiet threshold written into the fabric of space and time. One of the most fascinating aspects of the event horizon is that it is not a physical object. Instead, it is a mathematical boundary defined by escape velocity. At this distance from the black hole, the escape velocity equals the speed of light. Since nothing can travel faster than light, escape becomes impossible. For a distant observer watching from far away, objects falling toward a black hole appear to slow down as they approach the event horizon. Their light becomes increasingly redshifted, stretched to longer wavelengths by the intense gravity. Over time, the object seems to fade and freeze near the boundary, never quite crossing it from the observer's perspective. Yet, for the object itself, the experience is very different. According to the laws of physics, as we understand them, crossing the event horizon would feel unremarkable at first, especially for a very large black hole. There would be no sudden jolt or signal marking the crossing. The traveler would pass the event horizon without immediate awareness that anything special had occurred. This difference in perspective highlights one of the deepest ideas in modern physics, that time and space are not absolute. Near a black hole, time slows relative to distant observers, a phenomenon predicted by Einstein's theory of general relativity. Gravity does not merely pull on objects, it reshapes time itself. Event horizons also play a central role in one of the greatest puzzles in science, the black hole information paradox. According to quantum physics, information about physical systems cannot be destroyed. Yet, if information falls into a black hole and becomes inaccessible beyond the event horizon, it seems to vanish from the observable universe. Physicists have spent decades exploring this paradox, seeking ways to reconcile general relativity with quantum mechanics. Some theories suggest that information is somehow preserved on the surface of the event horizon, encoded in subtle quantum effects. Others propose that information may escape slowly over time through a process known as Hawking radiation. Hawking radiation is an incredibly gentle phenomenon. Black holes are not entirely black. They emit tiny amounts of thermal radiation due to quantum effects near the event horizon. Over unimaginably long time scales, this radiation causes black holes to lose mass and eventually evaporate. For stellar and supermassive black holes, this process takes far longer than the current age of the universe. The radiation is so faint that it has not yet been directly observed. Still, the idea that black holes can slowly fade away adds a poetic dimension to their story, reminding us that nothing in the universe is truly permanent. The size of an event horizon depends on the mass of the black hole. For a stellar black hole with several times the mass of the Sun, the event horizon may span only a few kilometers. For a supermassive black hole, it can be larger than the orbit of some planets, encompassing vast regions of space. Despite their name, event horizons are not necessarily violent places. The most extreme forces inside a black hole occur much deeper, near the central singularity. The event horizon itself is simply the point where escape becomes impossible, a quiet boundary marking the limits of observation. Modern astronomy has found indirect ways to study event horizons. By observing how matter behaves near black holes, scientists can test predictions of relativity under extreme conditions. High-energy emissions, gravitational waves, and detailed imaging all contribute to this growing understanding. The detection of gravitational waves from merging black holes has opened an entirely new way of studying event horizons. When two black holes spiral together and merge, their event horizons join and settle into a new shape. The ripples in spacetime produced by this process carry information about gravity itself. These discoveries highlight how black holes, once considered purely theoretical curiosities, have become central to modern astrophysics. They are laboratories for extreme physics, offering insights that cannot be obtained anywhere else. As you rest, imagine the event horizon not as something frightening, but as a gentle boundary between the known and the unknown. It represents the edge of what can be observed, a reminder that the universe still holds mysteries beyond our current reach. There is comfort in this idea. The universe does not reveal everything at once. It invites curiosity, patience, and wonder, allowing knowledge to unfold slowly over time. As your breathing settles into a slow, steady rhythm, let us drift gently toward one of the most curious ideas associated with black holes. It has an unusual name, but the concept behind it reveals something elegant about gravity itself. This phenomenon is known as spaghettification, and despite its playful sound, it describes a real and measurable effect predicted by physics. Spaghettification occurs because gravity does not pull equally on all parts of an object. The closer something is to a massive body, the stronger the gravitational pull becomes. Near a black hole, this difference in gravitational strength across even small distances can become extreme. Imagine an object falling feet first toward a black hole. The feet, being closer to the black hole, feel a stronger gravitational pull than the head. This difference creates tidal forces that stretch the object lengthwise while compressing it sideways. Over time, the object becomes elongated, like a long strand gently pulled apart. These tidal forces are not unique to black holes. They occur everywhere gravity exists. Earth's tides are caused by the moon's gravity pulling more strongly on the side of Earth closest to it. In black holes, however, these forces are dramatically amplified. The intensity of spaghettification depends on the size of the black hole. For smaller black holes, especially stellar mass ones, tidal forces near the event horizon are extremely strong. An object approaching such a black hole would experience intense stretching well before crossing the event horizon. For supermassive black holes, the experience is surprisingly different. Because their mass is spread over a much larger region, the tidal forces at the event horizon are comparatively gentle. In theory, an object could cross the event horizon of a supermassive black hole without immediate spaghettification. This counterintuitive idea highlights an important truth about gravity. It is not just the amount of mass that matters, but how that mass is distributed in space. Larger black holes can be, in some ways, more forgiving at their boundaries than smaller ones. Spaghettification is not an instantaneous event. It unfolds gradually as an object falls closer and closer to the black hole. The stretching increases steadily, guided by the mathematical laws of general relativity. As this stretching occurs, time itself behaves strangely. Signals sent from different parts of the object become increasingly distorted. Communication between the stretched regions becomes impossible as gravity disrupts the flow of information. Although this process sounds dramatic, it is governed by precise equations that scientists understand remarkably well. The same equations that describe planetary orbits and the bending of light also predict these extreme effects near black holes. Importantly, spaghettification does not violate any known physical laws. It is simply gravity doing what it always does, but under conditions far more intense than anything we encounter in everyday life. In astronomy, tidal forces also play a role in shaping galaxies and star systems. Black holes can tear apart stars that venture too close, creating luminous streams of gas that spiral inward. These events, known as tidal disruption events, produce brilliant flares of light observable across vast cosmic distances. Such observations allow scientists to study black holes indirectly. By watching how stars are stretched and heated, astronomers can estimate the mass and spin of the black hole involved. Even destruction, in this sense, becomes a source of knowledge. Despite these dramatic interactions, black holes spend most of their existence quietly influencing their surroundings. Tidal forces shape orbits, guide the flow of gas, and help regulate the growth of galaxies over billions of years. The concept of spaghettification also reminds us that the universe operates smoothly and continuously. There are no sharp edges or sudden breaks in physical law. Even at the most extreme boundaries, nature follows consistent rules. As you imagine these gentle stretches and flows, it may help to think of spacetime itself as a flexible fabric. Gravity does not pull objects through space alone. It reshapes the stage on which all motion occurs. This view of the universe, calm and interconnected, offers a peaceful perspective. Even phenomena that sound dramatic are expressions of deeper harmony governed by elegant principles. As your thoughts drift gently onward, let us now explore how black holes interact with something deeply familiar and yet endlessly mysterious: light. Light travels at the fastest speed allowed in the universe, and still, even, it must obey the quiet authority. According to Einstein's theory of general relativity, gravity is not simply a force pulling objects together. Instead, it is the curvature of space-time itself. Massive objects, like stars and planets, gently curve space-time around them. Black holes, with their immense concentration of mass, create some of the deepest curves imaginable. When light passes near a black hole, it does not travel in a straight line. Instead, it follows the curved geometry of space-time, bending as it goes. This effect is known as gravitational lensing, and it occurs throughout the universe wherever massive objects exist. In everyday space, gravitational lensing is subtle. Light from distant stars may bend slightly as it passes galaxies or clusters of galaxies, creating faint distortions or multiple images. Near a black hole, however, this bending becomes profound. Light that passes close enough to a black hole can be deflected into looping paths. In some cases, photons may orbit the black hole temporarily, tracing graceful circles before escaping back into space. This region is called the photon sphere. The photon sphere lies just outside the event horizon. It represents a delicate balance between light's forward motion and gravity's inward pull. Within this narrow region, light can circle the black hole one or more times. The existence of the photon sphere contributes to one of the most iconic images in modern astronomy: the silhouette of a black hole. When scientists captured the first image of a black hole's shadow in 2019, they were seeing light bent and trapped by gravity on cosmic scales. That image came from the supermassive black hole at the center of the galaxy Messier 87. The glowing ring around the dark center is not the event horizon itself, but light from hot gas swirling nearby, distorted by gravitational lensing. This bending of light allows astronomers to study black holes without seeing them directly. By analyzing how light behaves near these objects, scientists can infer their mass, spin, and orientation. Light approaching the event horizon faces an irreversible fate. At the boundary itself, the escape velocity equals the speed of light. Once crossed, even photons cannot return to the wider universe. To a distant observer, however, something curious happens. Light emitted by an object falling toward a black hole appears to slow and fade. The light becomes increasingly redshifted, stretched to longer wavelengths by the intense gravity. This gravitational redshift causes signals to lose energy as they climb out of the curved spacetime near the black hole. Over time, the object appears frozen near the event horizon, its light dimming into darkness. From the perspective of the falling object, time flows normally. There is no sudden pause or dramatic flash at the horizon. This difference in perspective highlights the subtle nature of time itself in strong gravitational fields. Gravitational lensing near black holes also creates echoes of light. Some photons take longer paths around the black hole before reaching observers, arriving slightly later than others. These delays provide additional clues about the black hole's structure. In regions with active black holes, light from surrounding gas is often polarized by strong magnetic fields. Studying this polarization helps scientists understand how black holes influence their environments and power energetic phenomena like jets. These jets, which we will explore more fully later, can extend for thousands of light years. They shine across the electromagnetic spectrum, from radio waves to gamma rays, driven by the complex dance of gravity, light, and magnetism. Light is also affected by the rotation of black holes. Spinning black holes drag spacetime itself around them, a process called frame dragging. This twisting further alters the paths that light can take. Near a rapidly rotating black hole, light paths become asymmetric. One side of the black hole appears brighter than the other due to relativistic effects that boost light traveling toward the observer. These effects are subtle, yet measurable. Each observation reinforces our understanding of gravity's quiet power. Despite their fearsome reputation, black holes do not actively pull light inward like cosmic vacuum cleaners. Light only falls in if it is already on a path that leads to close. Otherwise, it can pass by, bent but unharmed. This calm perspective is important. Black holes are not chaotic destroyers, but predictable features of the universe. Their influence is profound, yet governed by consistent laws. As you imagine light tracing smooth curves Through space, picture the universe as a vast, gently flowing tapestry. Even darkness plays a role in shaping its beauty. As the universe continues its quiet motion, we now turn toward another subtle and fascinating aspect of black holes. Their spin, rotation, is common throughout the cosmos. Planets spin, stars rotate, galaxies turn slowly over billions of years. Black holes are no exception. When a massive star collapses to form a black hole, it often retains the angular momentum it had during its life. Just as an ice skater spins faster when pulling in their arms, collapsing matter spins more rapidly as it shrinks. The result is a rotating black hole. A spinning black hole is described by a property called angular momentum. Along with mass and electric charge, it is one of the few measurable characteristics of a black hole. This simplicity is sometimes called the no-hair theorem, meaning black holes are remarkably simple objects. The rotation of a black hole has gentle but profound effects on the space around it. According to general relativity, a rotating mass drags spacetime along with it. This phenomenon is known as frame dragging. Frame dragging near a black hole is extreme. Space itself is pulled into a slow whirlpool around the black hole, twisting as it flows inward. Objects near the black hole cannot remain still relative to distant stars. They are compelled to move along with space-time. This effect creates a region outside the event horizon called the ergosphere. Within the ergosphere, space-time moves faster than light relative to distant observers. Although locally, the laws of physics remain intact. Inside the ergosphere, it is impossible for an object to remain stationary. Everything must rotate in the same direction as the black hole. This enforced motion opens a door to intriguing physical processes. One such process is energy extraction. In theory, particles entering the ergosphere can split, with one falling into the black hole and the other escaping with more energy than it had initially. This is known as the Penrose process. Although this process is difficult to observe directly, it highlights how black holes can influence their surroundings in surprising ways. They are not merely endpoints, but active participants in cosmic energy flows. The spin of a black hole also affects the location of its event horizon. For a non-rotating black hole, the horizon is a perfect sphere. For a rapidly rotating one, the horizon becomes slightly flattened, bulging at the equator. Rotation allows matter to orbit closer to the black hole without falling in. The innermost stable, circular orbit, or ESCO, moves inward as spin increases. This means that matter in accretion disks can orbit at higher speeds and temperatures. These hotter inner disks emit more energy, often in X-rays, making spinning black holes some of the brightest objects in the universe. Their activity powers quasars and luminous galactic cores. Spin also plays a role in shaping the powerful jets launched from some black holes. Magnetic fields anchored in the accretion disk can tap into the black hole's rotational energy, channeling it outward along the poles. These jets travel at nearly the speed of light and can stretch across intergalactic space. Despite their immense scale, they originate from regions smaller than our solar system. The orientation of a black hole's spin influences how we observe it. If the spin axis points toward Earth, the emitted radiation can appear brighter due to relativistic beaming, an effect important in astronomy and cosmology. Over time, black holes can gain or lose spin. Accreting matter from a disk can increase rotation, while collisions with other black holes can alter spin, direction, and speed. When two black holes merge, their spins combine in complex ways. The final black hole may recoil slightly, receiving a gentle kick through space due to asymmetric gravitational wave emission. Gravitational waves themselves carry information about spin. By analyzing these ripples in spacetime, scientists can infer how fast and in what direction black holes were spinning before they merged. Spin also influences how time flows near a black hole. The twisting of spacetime causes clocks near the rotating black hole to tick differently depending on their position and direction of motion. Despite these dramatic effects, the rotation of black holes unfolds quietly, governed by precise equations rather than chaos. Their spin is a steady, persistent feature, shaping space with calm consistency. It is comforting to realize that even in the most extreme environments, the universe follows orderly patterns. Rotation, gravity, and time weave together in predictable ways. As you let your thoughts drift, imagine spacetime gently turning like a slow cosmic current, guided by the presence of spinning black holes. As the universe continues its slow, graceful unfolding, black holes reveal another quiet role. Beyond their mystery and power, they act as subtle architects of galaxies themselves. Their influence stretches far beyond their immediate surroundings, shaping the long-term evolution of entire cosmic cities made of stars. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These giants can contain millions or even billions of times the mass of the Sun. Yet they occupy a region smaller than our solar system. Despite this compact size, their presence affects vast regions of space. Galaxies are not static collections of stars. They grow, merge, and change over billions of years. Supermassive black holes appear to grow alongside their host galaxies, suggesting a deep connection between the two. Astronomers have discovered a remarkable relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. The mass of the black hole correlates closely with the mass and motion of stars in the galaxy's central bulge. This connection suggests that black holes and galaxies evolve together, influencing one another through gentle feedback rather than violent control. One of the key ways black holes shape galaxies is through energy regulation. When matter falls toward a supermassive black hole, it often forms an accretion disk that shines intensely. This activity releases enormous amounts of energy into the surrounding space. This energy does not usually come from matter falling directly into the black hole, but from material heating up as it spirals inward. The released radiation and jets can heat nearby gas and push it outward. By doing so, black holes can slow or even stop star formation in their host galaxies. This process, known as feedback, prevents galaxies from forming stars too quickly or becoming overly dense. Without this regulating influence, galaxies might burn through their gas rapidly, leading to unstable growth. Black holes act as quiet moderators, helping galaxies maintain balance over cosmic timescales. In some galaxies, especially active ones, black holes produce enormous jets that stretch far beyond the galactic disk. These jets inject energy into intergalactic space, influencing the temperature and motion of gas between galaxies. This effect can prevent surrounding gas from cooling and collapsing into new stars, shaping not only one galaxy, but entire clusters of galaxies. Galaxy clusters contain hundreds or thousands of galaxies bound together by gravity. At their centers often lie massive galaxies with extremely active black holes that influence the entire cluster environment. Even though black holes occupy such small volumes, their energy output can exceed that of all the stars in their host galaxies combined during active phases. Over time, as black holes consume surrounding material, their activity may quiet down. Many supermassive black holes today are relatively calm, including the one at the center of the Milky Way, our galaxy's central black hole. Sagittarius A*, is currently in a low activity state. It quietly influences nearby stars without dramatic flares or jets, offering a peaceful example of a mature galactic center. Galactic mergers play an important role in black hole growth. When two galaxies collide and merge, their central black holes eventually spiral toward each other, forming a binary system. Over millions of years, these black holes lose energy through interactions with surrounding stars and gas, eventually merging into a single, larger black hole. The final merger releases powerful gravitational waves, rippling through spacetime and carrying information about the masses and spins involved. After merging, the newly formed black hole can influence the newly formed galaxy's structure, helping settle stars into stable orbits. Black holes also influence the distribution of dark matter indirectly. By shaping the movement of gas and stars, they affect how matter clumps within galaxies. Dark matter, though invisible, forms the gravitational backbone of galaxies. The visible structures we see are shaped by the combined effects of dark matter, gas dynamics, and black hole feedback. Over billions of years, this interplay leads to the diversity of galaxy shapes we observe today. From elegant spirals to massive, elliptical galaxies, even the largest structures in the universe, known as cosmic filaments, are indirectly shaped by black hole activity through galaxy formation and evolution. Black holes do not act quickly. Their influence unfolds gradually, often over timescales longer than the age of human civilization by factors of millions. This slow influence aligns beautifully with the calm rhythm of the universe. Nothing is rushed. Change comes steadily, guided by gravity and energy exchange. It is comforting to realize that black holes, often imagined as destructive forces, are also creators of structure and balance. They help determine when stars form, how galaxies grow, and how cosmic neighborhoods evolve. From this perspective, black holes are not threats, but integral elements of the universe's long-term harmony. As you continue to relax, imagine galaxies drifting quietly through space, their central black holes guiding their evolution with subtle precision. Black holes do not shine. They emit no light of their own, and they reveal no surface to reflect a glow. And yet, despite this deep invisibility, humanity has learned how to sense their presence with remarkable clarity. This quiet achievement comes not from seeing black holes directly, but from patiently observing how they shape everything around them. Astronomy has always been an art of indirect understanding. Long before black holes were confirmed, scientists inferred the existence of unseen planets and stars by watching how visible objects moved. Black holes fit naturally into this tradition of careful listening rather than direct viewing. One of the simplest ways astronomers detect a black hole is by watching stars. In some regions of space, stars orbit something massive that emits no light. These stars move at extraordinary speeds, tracing tight paths around an invisible center. By measuring these orbits, scientists can calculate the mass of the unseen object pulling on them. When the mass is immense, yet the region is incredibly small and dark, a black hole becomes the most reasonable explanation. This method has been used to study the supermassive black hole at the center of the Milky Way. For decades, astronomers tracked the motion of stars near Sagittarius A*. The precision of their orbits revealed a massive object packed into a tiny volume. Another powerful method comes from light itself. Although black holes are dark, the material around them can glow brilliantly. Gas and dust falling toward a black hole form accretion disks that heat up through friction and gravity. These disks emit light across many wavelengths, including visible light, ultraviolet radiation, and X-rays. Space-based observatories are especially important for detecting high-energy radiation that cannot pass through Earth's atmosphere. X-ray emissions are particularly useful in identifying black holes in binary systems. In these systems, a black hole pulls material from a companion star. As the material spirals inward, it heats up and emits X-rays, revealing the black hole's presence. The brightness and variability of these X-rays offer clues about the black hole's mass and spin. Sudden flares and steady emissions tell a story of matter moving under extreme gravity. Radio astronomy also plays a crucial role. Some black holes produce jets of charged particles that emit radio waves as they travel through space. These jets can extend far beyond their host galaxies. By mapping radio emissions, astronomers can trace the shape and direction of these jets, gaining insight into the black hole's orientation and activity. One of the most remarkable achievements in modern astronomy came when scientists produced the first image of a black hole's shadow. This was accomplished not by a single telescope, but by a global network working together. The Event Horizon Telescope linked radio observatories across Earth to create a virtual telescope the size of the planet. This technique, known as Very Long Baseline Interferometry, allowed unprecedented resolution. The image did not show the black hole itself, but the dark silhouette it casts against the glowing material around it. This shadow matched predictions made by Einstein's theory of general relativity, confirming decades of theoretical work. Gravitational waves opened an entirely new way of observing black holes. These gentle ripples in space-time are produced when massive objects accelerate, especially during black hole mergers. Detectors on Earth can sense distortions smaller than the width of an atom caused by events billions of light-years away. These measurements allow scientists to hear black holes colliding. Gravitational waves carry information about the masses, spins, and distances of merging black holes. Each detection adds a new piece to the story of how black holes form and evolve. Unlike light-based observations, gravitational waves pass through matter almost untouched. This allows them to reveal events hidden behind dust or occurring in regions otherwise invisible. Time itself becomes a tool for observation. The way signals arrive, stretch, or repeat reveals how spacetime is curved by massive objects. Delays and distortions offer clues about gravity's strength and structure. Computer simulations play a vital role in interpreting observations. Scientists model how matter behaves near black holes, comparing simulated data with real measurements to refine their understanding. These simulations are grounded in physics but refined through observation, creating a quiet dialogue between theory and reality. Artificial intelligence and machine learning now assist astronomers in sorting vast amounts of data. These tools help identify subtle patterns that might otherwise be missed. Despite all these techniques, black holes remain partially mysterious. Observations provide boundaries and behaviors rather than direct access. This balance between knowledge and mystery keeps the field alive and evolving. Importantly, black hole research drives innovation beyond astronomy. Technologies developed for space observation influence medicine, communications, and computing. In education, black holes serve as gateways to curiosity. They inspire interest in physics, mathematics, and the nature of reality itself, making them powerful tools for learning. Even though black holes are distant and extreme, the methods used to study them are calm, methodical, and patient. Progress comes through careful accumulation rather than sudden revelation. This gentle pace mirrors the universe itself. Discovery unfolds slowly, guided by observation rather than force. As you rest, imagine astronomers quietly listening to the cosmos, gathering whispers of gravity and light across vast distances. Black holes do not need to be seen to be understood. They speak through motion, energy, and time. Black holes are not only objects in space. They are quiet, testing grounds for the laws of physics themselves. In their presence, ideas that work beautifully elsewhere begin to stretch, bend, and sometimes gently fail. This is not a violent collapse of knowledge, but a calm reminder that our understanding is always incomplete. Most of what we know about black holes comes from Einstein's theory of general relativity. This theory describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. For planets, stars, and galaxies, it works with extraordinary precision. Near a black hole, however, spacetime becomes curved to an extreme degree. Paths that were once straight bend sharply. Time slows. Distances compress. The equations still function, but they point toward conditions unlike anything else in the universe. At the very center of a black hole lies what physicists call a singularity. According to current theory, this is a point where density becomes infinite and space-time curvature has no upper limit. the laws of physics, as we know them, stop providing clear answers. It is important to understand that a singularity is not necessarily a physical object. Rather, it signals the limits of our mathematical descriptions. It is a place where existing theories cannot fully describe reality. Quantum mechanics, the theory governing the smallest scales of nature, works exceptionally well for atoms and particles. General relativity works exceptionally well for massive objects and cosmic scales. Black holes sit at the intersection of these two frameworks. This intersection creates a quiet tension in physics. When matter is compressed to extreme densities, quantum effects should matter. But general relativity does not include quantum behavior. Physicists believe that a deeper theory, often called quantum gravity, may resolve this conflict. Such a theory would unify gravity with the other fundamental forces of nature. Black holes provide natural laboratories for testing ideas about quantum gravity. Although direct access to their interiors is impossible, subtle effects near their edges may offer clues. One such effect is Hawking radiation. This phenomenon arises from quantum effects near the event horizon. According to theory, black holes are not entirely black. Tiny amounts of energy can escape due to fluctuations in quantum fields. Over extremely long timescales, this radiation causes black holes to lose mass and slowly evaporate. For stellar mass black holes, this process takes far longer than the current age of the universe. For supermassive black holes, evaporation times are almost unimaginably long. Hawking radiation introduces deep questions about information. If black holes evaporate, what happens to the information carried by the matter that fell into them? In physics, information is considered fundamental. The laws of quantum mechanics suggest that information cannot be destroyed. Yet black holes seem to hide information behind their event horizons. This puzzle is known as the black hole information paradox. It has inspired decades of research and debate, involving some of the most brilliant minds in science. Several proposed solutions suggest that information may be encoded on the event horizon itself, stored in subtle correlations. This idea connects black hole physics with concepts from thermodynamics and entropy. Entropy measures disorder, or the number of possible microscopic states of a system. Black holes have entropy proportional to the area of their event horizons, not their volume. This surprising relationship hints that the universe may store information in unexpected ways. Some physicists even suggest that reality itself may have a holographic nature. In this view, information inside a region of space could be encoded on its boundary. Black holes offer the clearest example of this principle. Time also behaves strangely near black holes. From the perspective of a distant observer, objects falling toward the event horizon appear to slow down and fade. For the falling object itself, time passes normally. This difference in perspective reveals that time is not absolute, but shaped by gravity. Black holes force us to accept that space and time are flexible, responsive, and deeply interconnected. Even causality, the idea that causes precede effects, takes on a subtle complexity near event horizons. Certain paths through spacetime become inaccessible, creating regions permanently cut off from the rest of the universe. Despite these strange effects, black hole physics remains grounded in careful reasoning and observation. Speculation is guided by mathematics, experiments, and data. The calm pace of progress reflects the patience required to understand such profound phenomena. Answers emerge slowly, refined through decades of work. Black holes remind us that mystery is not a failure of science, but an invitation. Each unanswered question points toward deeper layers of understanding. In education and research, black holes inspire curiosity across disciplines, from physics and mathematics to philosophy and technology. They challenge us to think differently about reality while remaining humble about what we do not yet know. As you rest, imagine the laws of nature gently stretching at the edges of understanding, not breaking violently, but bending softly. Black holes are where certainty fades into wonder, and where calm curiosity continues its quiet journey. Black holes are not only shaped by space, they are shaped by time. To understand them fully, it helps to imagine their quiet journey across the vast history of the universe. From the earliest moments after the Big Bang to eras far beyond the present day. In the early universe, conditions were very different from what we see now. Matter was hotter, denser, and more evenly distributed. Stars had not yet formed. Galaxies had not yet taken shape. Space itself was still expanding rapidly. The first black holes may have formed surprisingly early. Some theories suggest that small black holes could have emerged from density fluctuations shortly after the Big Bang. These hypothetical objects are called primordial black holes. Primordial black holes, if they exist, would not form from collapsing stars. Instead, they would arise from extreme concentrations of energy in the early universe. Their masses could range from tiny to enormous. While no direct evidence has yet confirmed primordial black holes, scientists continue to search for subtle signatures they might leave behind, such as gravitational lensing effects or unusual radiation patterns. As the universe cooled, the first stars began to form. These early stars were massive and short-lived, composed almost entirely of hydrogen and helium. When they reached the end of their lives, many likely collapsed into black holes. These early stellar black holes may have served as seeds for larger structures. Over time, through mergers and accretion, they could grow into intermediate mass black holes. The formation of supermassive black holes remains one of the most fascinating puzzles in astronomy. Observations show that massive black holes existed when the universe was less than 1 billion years old. Growing a black hole to millions or billions of solar masses so quickly challenges simple models of steady growth. This suggests that alternative formation pathways may have played a role. Some theories propose that large gas clouds in early galaxies collapsed directly into massive black holes, bypassing the usual star formation process. These are known as direct collapse black holes. As galaxies formed and evolved, black holes became deeply intertwined with their host systems. Nearly every large galaxy appears to contain a supermassive black hole at its center. The growth of galaxies and black holes seems to be connected. Observations reveal correlations between the mass of a galaxy's central black hole and the properties of its stars. This relationship suggests a quiet feedback process. As black holes accrete matter and release energy, They influence star formation, gas distribution, and galactic structure. In this way, black holes play a subtle but important role in cosmic evolution. They are not merely passive endpoints, but active participants in shaping the universe. When galaxies collide, their central black holes eventually spiral together. These mergers produce gravitational waves, ripples in spacetime that carry energy outward at the speed of light. In recent years, detectors on Earth have begun observing these waves directly. Gravitational wave astronomy has opened a new window onto black hole history. It allows scientists to study events that emit little or no light. Each detection offers clues about black hole masses, spins, and formation environments, helping to reconstruct their past. Looking toward the future, black holes will continue their slow evolution. Stars will age and die. Galaxies will change shape. Black holes will keep accreting matter and merging. On extremely long timescales, longer than the current age of the universe by many orders of magnitude, Hawking radiation becomes significant. As black holes lose mass through this process, they will eventually evaporate completely, leaving behind faint traces of energy. This distant future is almost impossible to visualize. Stars will have burned out, galaxies may drift apart. The universe will grow colder and darker. Yet even then, black holes play a role in shaping cosmic destiny. Their slow evaporation marks one of the final chapters in the story of matter. Time around black holes also offers insights into the nature of aging and change. Near an event horizon, time slows relative to distant observers. This effect has been confirmed indirectly through observations of objects near massive gravitational fields. It reflects the deep connection between gravity and time. In a sense, black holes act as cosmic clocks, revealing how time flows differently depending on location and motion. From the birth of the universe to its far future, black holes accompany cosmic evolution like silent witnesses. They emerge from the depths of stars, shaped galaxies, test physical laws, and eventually fade away. Their existence reminds us that the universe is not static. It is a story unfolding over immense spans of time. As you relax, imagine black holes drifting gently through cosmic eras, unchanged in their calm presence, even as everything around them transforms. Black holes may seem impossible to study at first. They do not emit light in the usual way, and they cannot be visited directly. Yet, through patience, creativity, and gentle observation, scientists have learned how to study these quiet giants with remarkable detail. One of the most important tools for studying black holes is light itself, not from the black hole, but from its surroundings. When gas and dust fall toward a black hole, they form an accretion disk. This disk heats up as particles collide and accelerate. Temperatures can rise so high that the material glows brightly across the electromagnetic spectrum. Astronomers observe this light using telescopes sensitive to radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each wavelength reveals a different layer of information. X-ray telescopes are especially useful for studying black holes. The inner regions of accretion disks emit intense X-rays as matter spirals inward at extreme speeds. Space-based observatories, such as Chandra and XM Newton, orbit above Earth's atmosphere to capture these high-energy signals with clarity. Radio telescopes provide another calm window into black hole environments. They can observe jets of particles launched from the regions near black holes at nearly the speed of light. These jets can extend for thousands or even millions of light years, shaping the surrounding galaxy and influencing star formation. In 2019, humanity saw the first direct image of a black hole's shadow. This achievement came from the Event Horizon Telescope, a global network of radio telescopes working together. By combining data from observatories across Earth, scientists effectively created a planet-sized telescope. The image revealed a glowing ring surrounding a dark center, consistent with predictions from general relativity. It was a quiet confirmation of decades of theory. Gravity itself also serves as a tool for studying black holes. When a black hole passes in front of a distant star, its gravity bends the star's light. This effect, called gravitational lensing, can magnify and distort the appearance of background objects. Careful measurements of this distortion reveal the black hole's mass. In binary systems, black holes reveal themselves through motion. When a visible star orbits an unseen companion, astronomers can calculate the mass of the hidden object. If that mass exceeds the theoretical limit for neutron stars, the companion is identified as a black hole. Gravitational wave observatories represent one of the most peaceful yet powerful methods of black hole study. Facilities like LIGO and Virgo detect tiny vibrations in spacetime. These vibrations occur when massive objects, such as black holes, spiral together and merge. The signals are brief, lasting fractions of a second, but they carry immense information about the objects involved. From these waves, scientists can determine the masses, spins, and distances of merging black holes. This method allows observation of black holes that emit no light at all, expanding our understanding beyond visible matter. Computer simulations also play a vital role. Using advanced models, researchers recreate black hole environments, testing how matter behaves under extreme gravity. These simulations help interpret observations and refine theories, bridging the gap between mathematics and reality. Artificial intelligence and machine learning are increasingly used to analyze large data sets. These tools help identify patterns and signals that might otherwise go unnoticed. Technology, quietly and steadily, brings black holes into focus without disturbing their calm existence. Future observatories promise even deeper insights. Next-generation space telescopes and gravitational wave detectors will observe black holes with greater sensitivity. Some will study the early universe, searching for the first black holes ever formed. Others will map black hole populations across cosmic time, revealing how they grow and interact with galaxies. Through light, gravity, and thoughtful innovation, black holes become less mysterious, yet no less awe-inspiring. They remain distant and silent, but not unreachable. As you settle deeper into rest, imagine these instruments gently listening to the universe, translating subtle signals into understanding. Black holes are more than distant cosmic objects. They are ideas that gently reshape how we understand reality, time, and our place in the universe. For centuries, humans have looked at the night sky and wondered what lies beyond the stars. Black holes represent one of the deepest answers to that curiosity. They show us that space is not empty, time is not fixed, and gravity is far more powerful and subtle than everyday experience suggests. At the heart of every large galaxy, including our own Milky Way, sits a supermassive black hole. These quiet centers influence how galaxies form, grow, and evolve. Rather than destroying galaxies, most black holes help regulate them. Their energy output can slow or trigger star formation, shaping cosmic balance. This gentle control reminds us that even the most extreme forces can contribute to harmony over vast timescales. Black holes also test the limits of physics. They are places where general relativity and quantum mechanics meet, yet do not fully agree. Understanding black holes may one day lead to new theories that unify these two pillars of science. In this way, black holes are teachers. They guide human knowledge forward, inviting patience, humility, and creativity. They also offer perspective. Compared to cosmic scales, human life is brief. Yet our ability to understand such vast phenomena is remarkable. From a small planet orbiting an ordinary star, we have learned to detect ripples in spacetime and shadows cast by invisible giants. This achievement reflects the quiet power of curiosity and cooperation. Black holes inspire art, philosophy, and storytelling. They appear in literature, film, and music as symbols of mystery and transformation. Yet the real black holes are calmer than fiction suggests. They do not chase or threaten. They simply exist following the laws of nature. Their calmness mirrors the universe itself, vast and patient, unfolding over billions of years. For those seeking relaxation or sleep, black holes offer a paradoxical comfort. Their immense scale makes everyday worries feel lighter. Their steady presence reminds us that change is slow. Cycles are natural, and the universe continues, regardless of momentary concerns. Even time behaves differently near black holes, stretching and slowing. This idea invites us to release urgency and rest in the present moment. As technology advances, black holes will continue to reveal their secrets. New observations will refine what we know and challenge what we assume. Yet some mystery will always remain, and that is part of their beauty. Science does not remove wonder, it deepens it. As this gentle journey comes to a close, imagine the universe resting as well. Stars burning quietly, galaxies drifting, black holes waiting, timeless and still. Let your thoughts slow, like matter approaching an event horizon, not falling, but settling into calm. You are part of this universe, connected to its rhythms and laws. May this sense of scale and serenity stay with you as you drift into rest. Thank you for spending this quiet time exploring the universe. Sleep well.